I can start. It's good time. So good morning. So this is the last lecture. And so I will recap a little bit where we were yesterday, okay? So yesterday I introduced the model of an interface, elastic interface, pulled with an external force F. And then we worked a little bit and we end up on a discrete model that I draw here. So the height of the interface is this axis, and in pink you see the interface in one dimension, okay? And so what I want to draw here is the fact that in our model is discrete because there are narrow wells, and the interface, each block of the interface is pinned in one of the narrow wells, which are sticky places, and there is a threshold that you have to overcome in order to move, for example, to move from here to here, okay? And so this is, these are 1, 2, 3, 4, 5, 6 blocks. In general, we will have L blocks. And we are interested in the limit L goes to infinity, okay, a large number of blocks. So they are characterized by a height H1, H2, HL, which is now discrete, okay? And so what I told you to explain this model is that now the randomness is given by the distance between the wells, and this distance is called delta, and we said that there is G delta is the PDF of the distance between two consecutive wells. GD delta is not a particular feature, okay? So it's not a power law, it's something that you can imagine G of delta. This is an example, okay? Is exponential minus delta. Distribution, positive, it cannot be negative distance, okay? But this is only requirement, and the results are independent. I mean, the universal results are independent of G of delta. Now, what I told you is that the relevant quantity is, let's call it xi. This is the distance, let me say, is the distance to the instability threshold. Okay. So is x for the block I, it will be xi. So the threshold is 1. We said all these patches as a threshold equal to 1. So you need that the sum of the other forces are bigger than 1 in order to make this unstable. And so what you say is that is 1 minus the elastic forces. For this one-dimensional model, it will be the elasticity induced by the two neighbors of the site I. And then there is the external force. So you sum the two forces that try to pull the block, and one is the threshold, okay? If xi is positive, I is the block I is stable. And if xi is negative, then the block I is unstable, okay? The block is unstable. what happens is that this block will move here, and this change xi. And this change also the two neighbors, which become more unstable. Okay, and this can propagate in an avalanche. Okay, and then we said, okay, instead of studying this model, which is one dimension with short range with the Laplacian, we study a model which is different. So let me write it here. Is the fully connected model. And the only difference is that this is the average position of the line. Cm means center of mass, is the average position of the line. And then you have the same thing as before, plus f. Okay? So this is the model that you can study analytically. Okay? You replace this by this. That's it. And then I couldn't, so if you look at the lecture which is associated to yesterday, I will show that it's possible to study the P of X, which is for a given force F, which is the distribution, the PDF if you want, the PDF of the Xi when L is infinity. Okay, you have a stationary distribution. Let me write stationary. And if you write the equation for this object, what you can get is V as a function of F. And you will see that there is a critical force Fc and something like this. This is the velocity as a function of the force. And you find, using this method, that the critical force is a function of my distribution where I wrote it G of delta. So knowing G of delta, you know the critical force, and you know the force, and you know that this is linear. Here is linear, and so this is the exponent is beta equal to 1, because the idea is that the velocity should go as F minus Fc power beta. And so for this mean field model, you have beta equal to 1. So this I didn't do. I let, if you want to do it, is a half a page of calculation, okay? And what we will do today is so in this model, the model that I wrote, it will be the same, but what I put in order to destabilize the system is the external force F. So if I'm stuck in a configuration, I increase the force F until one of the Xi become destabilized, then I stop to increase the force F, and I look at the avalanche which is propagated. And then at certain point, the system starts to move and there are no any more avalanches. So this is a protocol which is used a lot. It's called, let's say, in the depinning called force control, because you control the force. And in the yielding, it's called stress control, because you control the stress. So you move F, and you see what is going on, and you observe this transition, okay? Now, if you want to study the avalanches, the distribution of the avalanche depends on F. So the distribution that you measure at F equal Fc over 2 is different from the distribution that you measure at Fc. No, sorry. Plus minus 1 minus delta by 2. Okay, so this is because it was short range. In the case of the fully connected model, it will be all the other minus delta over L. Okay. So now, what you would like to do when you study the avalanches is to work at a force which is fixed, okay, and to produce avalanches at that force. And so this is possible, but you have to modify a little bit. And so this is called the displacement or strain control. So you move the interface, but you try to keep the same force. And so the difference is that you introduce, so you replace, so this is the same, but you introduce an elastic force that I can draw here. So you have some position W that you control. So what you move now is W. And when you pull W, there is an elastic spring which connects W to each one of the blocks. Okay, here you see there is an elastic spring, K0, that connects W to each one of the blocks. Okay? So when you increase W, so if we want to see when you increase W, the block HI as a force, this is the force acting on the block HI, increases, okay? And so it is, this object plays the same, is a force, dimensionally is a force, is an elastic force. And now you can see what is the average that we call FW is 1 over L. So this is the force acting on the unit length. So W is independent of I, so it will be A0 W minus H of the center of mass. So this is the force which acts per unit length on the interface, okay? Is the external force that you apply. And let's see what is going on as it is behaving, okay? This is F of W as a function of W. So let's say that we are stuck, like in the figure that is here. And so there is some value of W, let's say that is this one. So let's say that this is W equal to 0. Okay, and now we are stuck and we start to move up W. So the force is increasing because if you move W up, the force, it will increase. And this slope is K0, okay? You see, the center of mass doesn't move, the line is stuck, so W increases, okay? And the force acting on the interface increases until the moment that there is one point that becomes unstable. And in this case is the center of mass which starts to move a little bit. And now you stop because you do this in a quasi-static way, so W stop to evolve, okay? W is fixed. You let the avalanche, and the avalanche, so if there is an avalanche of size S, then the center of mass become center of mass plus S divided by L, okay, which is the number of blocks. And so this, you go down, okay? So the force F of W, when you are in this point, let me call this point W star, the F of W becomes F of W minus K0 S over L. So it jumps down, and this is K0 S over L. Let me do that. And then you continue to go up, then you go down. This is another avalanche. Then you go up, you go down, you go up, you go down, and so on. So you oscillate around a given value. And because the avalanches are divided by L, if the avalanche are not system size, when L goes to infinity, this noise will become smaller and smaller, and so you will see a flat line at a given force. And so when L goes to infinity, F of W is a number, okay, of W and K0 is a number. And this number, when K0 goes to 0, become the critical force. We will see that, okay? Well, here. So Xi. So Hi are here, are the position of the interface. Xi are the distance to the instability threshold. So you are here, and there is a well, and this well blocks you with some force which is equal to 1. And then you look at the force that are acting on this block, and you compare how they are compared to 1, okay? So if Xi is bigger than 0, it means that 1 wins against this force, you are pinned. If Xi is smaller than 0, you are unstable. This block move, so the block has plus delta. Hi, so Hi goes to Hi plus delta. This is what happens for the position. Now, here, if you put plus delta, the two, this goes plus, so this is gets stabilized and this gets unstabilized. Is clear the model? So you have the two words, the words of the X and the words of the H. Okay, so let's go back here. What? The first control, both are quasi-statically. For quasi-static, I means the following thing. You increase the parameter, and when there is an instability, you stop to increase the parameter, and you look what happens. Okay, this is very easy to do in numerical simulation, and is what we do. It's very difficult to do in experiments. So what they do in experiments is they increase their parameter with a velocity which is small, and then there is a huge amount of questions of where the avalanche stop. Because when you do the things quasi-statically, there is an instability that triggers other instabilities. You wait, and then the system is blocked, and you say, this is an avalanche. But if you increase the parameter while the avalanche is going on, then it's difficult to decide if the avalanche is over or not, if you start a new avalanche. So there is it's difficult from the experimental point of view. They see burst, but then to disentangle the avalanches is difficult, okay? In the simulation, it's easy. You do quasi-static protocol, okay? And so you measure, in the simulation, you really measure these jumps, and these are the avalanches, okay? And so the good point here is that when you put the parabolic potential, which is an elastic force, when you use the force, this is the force, then you are able to, let's say, have avalanches always at the same force. So this is the protocol that is used and that we will use today in order to see to study the avalanches, okay? So let me write now as a function. So let's say that we take one of the block as a function of my parameter W, and now we write again so these are all functions of W. I don't write it in order, but it's clear that for a given W, you have a stable state. Okay, and so now, so the position of the line and the center of mass also depends on W. And now let's do the following thing. We have all the blocks. So I goes from 1 to L. This is our variable that say how far we are from the instability. And we start from a situation where we are stable. So now they are all positive, okay? In this case, they are positive for all I, okay? For this value of W, all the xi is positive, which means the line is stuck in a given position, okay? And now we do the following things. We increase W of a small amount. When you increase W of a small amount, the force acting on the line increases. So everybody is pushed in the negative side. And then there are the possibility that some of them become negative, okay? And so now to study the avalanche, we have to split what is going on generation per generation. The first generation of instability is when the first become unstable, then they be stabilized, and the second generation are the one which become unstable because the first stabilized. So at each time that there is an instability, the block becomes stable and can destabilize other blocks. And so we divide them by generation. So let's look what is going on at the first generation. Let me say that we have a time of the avalanche, which is the time t equal to 1. Okay, and in this generation, HCM is constant. Okay, doesn't evolve, but W evolve in this way. So the total force here, or the total value of xi, decrease of delta W. Now we have two cases. You have that, what I call the stable blocks. Blocks, or let me write it, stable blocks. So what it means that xi of W is bigger than K0 delta W. If the position of your xi is bigger than the force you give more, it will remain stable, okay? So when you do the shift, let me write here t equal to 1 because this is what is going on at the first generation. Now that you have increased from W to delta W, this is equal to xi of W minus K0 delta W. Is it clear? So this, you added delta W, so this will just be shifted to the origin, okay? Nothing special. Now we have the unstable blocks. So the condition is that xi of W is smaller than K0 d delta W. So these guys will touch the origin, they become unstable, okay? K0 delta W is very small, so essentially they become 0. And so we can say that xi at time t equal 1 of these unstable sites is just the new position, okay? So you jump of delta, and now you have to be careful because there is hi here and hi here. So if hi jump of delta, then this is 1 plus k0. So it gets stabilized, it becomes positive again, okay? And there is this k0 plus because we changed the parameter. And now this is not all. We would like to know how many they are, these stable blocks, okay? And so let's imagine, so let me write it here. We have our distribution, PW of X. So this was the distribution when everybody was stable, okay? So it's a positive distribution, something, we don't know what it is a positive distribution. And now what you want to know is how many blocks verify this condition. Okay, delta W is very small. So essentially what you want to know is, let me say, the total fraction. So if this is K0 delta W, we want to know this area, okay? And this area, when delta W is small, is just P0, K0 delta W, okay? So because you are very close to, should be very close to the origin, you can just the Riemann integration, okay? And so this area, the fraction of unstable sites, are really the one which are very close to the origin. So you can say this area is just P0, K0 delta W, okay? It will be the integral between 0 and K0 plus delta W of P of X, but because the two are very close, you can approximate with this, okay? So this is the first generation. Now let's look at the second generation. This fraction of sites moved, where L is infinity, so there is a huge number of sites that move at the first generation. And the total, so now we are in the quasi-static protocol. So this is the time t equal 2. So W does not move anymore, or W plus delta W does not move anymore. So this term is fixed. But what moves, now the HI has moved, this we took into account, but what we didn't took into account is that now the center of mass has moved, okay? Because the interface moved, so the center of mass, let's say HCM at T equal 2, is equal to HCM at T equal 1, plus the total, so this is the center of mass, so we need the total fraction that has moved, and in average, how much they have moved. And in average, everybody moves, you see, of delta. So here there is no K0, so it's only HI has move of delta. There are a fraction of them that has move of delta. Delta is a random number. In average is delta bar. So this is delta bar P0, A0, dW. So it's the fraction of unstable times the displacement average of the unstable sites. Is clear? So this is what is going on. And then we have to redo what we did here. So what happens? There are two possibilities. Either the blocks are stable, So what is the condition? Now the condition is that a block xi of W is stable if it's bigger not just of K0 delta W, but of the sum of the two. So it will be 1 plus delta bar P0. So the two contribution, the one from delta W and the one from the motion of the center of mass, these are really the ones which are stable, okay? And if you are stable at time t equal 2, then you can compare what was happening at time t equal to 1. So you get this shift. Okay. And now if you go back at time t equal to 0, so at x I of W, it will be minus 1 plus delta bar P0 A0 dW. Okay? So this is what is going on for the stable blocks. So this is the result. Time t equal 2, you have a big shift. This is the shift of delta W. This is the shift induced by the first generation. Now, let's see what happens to the unstable blocks. We are almost there, right? So now the unstable blocks are the one which are smaller than this. And then what they do is they just are reinitialized to a value which is random. And now we have to compute what is the total fraction. Again, the total. So total means first generation plus second generation. Total fraction of restabilization. It will be the same thing, as the same reasoning as before. So we should now, instead of doing this area, the area will be all of this. So it will be P0, which is the height of the function, time the length, which is 1 plus delta bar PW0, K0 d delta. Okay? So now I'm done, okay? So now I'm done. Now you have to do the third generation and the fourth generation, the fifth generation, and so on. But what you realize is that every time you have a generation, you add this term to the so let me erase here. So yes, because again, the key point, every time when you compute this object, you should integrate P of Wx as from 0 to some value, which is, for example, K0 d delta W, and then you approximate it by P0, K0 dW. Then everything else is an high order correction, and this is because delta W is infinitesimal. So we are doing an infinitesimal perturbation, and so the distribution doesn't change too much because you are just picking a very small slice close to the origin, okay? And everything, you will see everything is of the order delta W, and these are numbers, and so it will remain small forever. I mean, we will see, not always, but it will, if it remains small, you can do it. And so what I mean is that we have to compute what is going on. This is the first generation. This is the second generation. This is the third generation. This is the first generation, and so on. This is 3. This is W, and so on, okay? Plus, these are all the generation, and so this is a geometric sum, and you can replace the sum of all generation in this way, okay? And so now we can write what is going on for the stable blocks, all the generation, okay? The blocks that were not part of the avalanche, okay? The stable blocks what they did, so now is after infinite time, so this is still the new blocked configuration, the new metastable state is related to the old metastable state up to a shift, which is K0 dW, and then we have to put this 1 minus delta bar PW0. Okay. This is the sum of all the generation of avalanches. And these are the blocks which were not part of the avalanche. And the unstable block they are just the one that are reinitialized. And their total fraction, is PW0 K0 dW, and then we have all the contribution, and we charge at this. Okay. So now that we have these two possibilities, we can write the equation of motion of PW. So if it's okay, I raise here, okay. So you understood what is going on. So it is important to understand what is going on at the first generation. Either the block is unstable, in which case W is increased and the block is just shift. Either the block is unstable, in which is reinitialized, and how many they are, it depends on the distribution, and so this is the amount. And then if you want to know the details, you have to do all the generation. So you replace these and this by something divided, the same thing divided by this, okay? This is how to account of all the generation of instabilities, but okay, is good already if you understand the first step. So now that we know what happens to a generic X when it goes from W to W plus delta U, we can write what is the full distribution. Okay? So now this X is X of W plus delta W, and we have to understand what is going on. We said there are two things that can go on. Either is the same distribution W, just that you have to shift XW in XW minus this, and this is X. So it means the XW is X plus this. So this is just the guys who were stable. What this means is that the distribution, this term, is just a, let's say that is here, for example, the distribution. You just make a translation to the origin, okay? This is PW, sorry, this is P of W. This is P of W plus delta W. You shift everybody to the origin, okay? This is what means this term. But now we have also to account of this term. So with this probability, P0, K0, delta W divided 1 plus minus delta bar PW0, this is the probability to be unstable. Then the value of X is, sorry, there is no bar here. The value of X is 1 plus K0 delta. Delta is distributed using G of delta. So we can say that G of delta d delta is equal to G of X divided 1 plus K0 dx divided 1 plus K0. And so we have this here, G of X divided 1 plus K0 divided 1 plus K0. You have to be careful because this comes from the Jacobian between d delta and dx. And so this is the equation, exact equation, for the propagation. So what happens when you change from W, so these two terms depends on W, and in W plus delta W, either nothing happens but you become more unstable, either you are unstable and then you are stabilized, okay? These are the two things that can happen. And now because delta W is small, we can develop this term. It will give you PW of X plus K0 d delta W 1 minus delta bar PW0 derivative respect to X of PWX. Okay? And then you can continue up to the other orders, but this is enough. And so what you have is now you have a differential equation here. There are the two terms which depends on delta W. Okay? And so let's reorganize everything. You will have the derivative with respect to W is equal to K0 divided 1 minus delta bar PW0. And then we have the derivative with respect to X of PWX. And we have what is left here, which is PW0, this term. This is already gone. And then we have G of X divided 1 plus K0. And here we can put 1 plus. What this is? This. 1, this is very small, so it's 1, yes. So what you want is to multiply this by 1 minus this, but is 1. You mean minus here? Actually, it's correctly normalized like this. So what you are is normalized correctly. Yes, I understand what you mean. Okay, I have to think more about. So what you mean is you have a term this times this, but actually, for some reason, it's not. Okay, I will think, but yes, actually everything is correctly normalized like this. But okay, let's is a good suggestion. I will think about it. But anyhow, because actually what I mean is that now so we spend a lot of work to find this term, and this term will be important at the end if I have time. Now it's not correct, this one, so is half an hour? No, 45 minutes? Again, 45 minutes, no? So if I have time, I will check this term. But now you see that at some point, you reach a fixed point here when this is equal to 0. Okay, when this in the brackets is equal to 0, it means that this derivative is equal to 0, and it means that the system doesn't evolve anymore if you move W. So somehow you reached the stationary state. So the equation for the stationary state is dx p of x, let's put the minus here, is equal to pw0 divided 1 plus k0 gx1 plus k0. Okay, and this, you say, okay, there is only one derivative, it's very simple, it's simple, but you have to remember that there is this term, okay, so you have, so this is the stationary equation, so let's put stationary, okay, so you have to fix the value of P0, okay, and to do that, you can say, okay, let's observe that if I take minus x dx px in dx from 0 to infinity, I can use the integration by parts, okay? And this will be a term which is 0 and then minus, okay? So, yes, I have it out now. Yes, dx px, which is equal to 1. Okay? Let me check if I have a problem of sign, but I don't think so. No, it's okay. So minus this is equal to 1. Do you agree? You do first the integration by parts, so the total derivative is equal to 0. And then you have this is derivative, this is the integral, and by the normalization of P dx, you get that this integral is 1, okay? So let's do this integrate over x on both sides. So you have minus the integral over x dxp equal, and then we have to do p0 1 plus k0, and then we have to integrate it over x, gx divided 1 plus k0, between 0, infinity, and we have to integrate it this, okay? And so this, we said, is 1, all of this. And this, so you see you have 1 pi k0 here. You need, so let me do the same thing, 1 plus k0. And then we have the integral in dz, gz, dz, okay, from 0 to infinity. And this is delta bar. Okay? And so we have that P0 is fixed, and is 1 over K0 plus 1 delta bar. Okay? So we solved this. Now the goal is to inject this here, and now is a standard differential equation that you can integrate. I give you the result. We will not use it a lot. Yes. Yes, but for the moment. So when you are subcritical, it's like this. If I have time, I will show what happens when you reach the denominator. But yes, for the moment, yes. So it means that delta, so what Anupam is saying, there was a denominator, which was K0, 1 minus delta bar P0, W, and this means that P0 W should be smaller than 1 over delta bar. And you see that this K0, at least in the stationary, if K0 is there and is positive, this satisfies. But this doesn't mean that during the evolution you cannot touch this instability, okay? And this is a very interesting question, and it is something that with a lot of physics. But for the moment, let's assume that everything go plain, like in a plain way. So you don't touch the denominator, you reach the stationary solution. Now I found what is the value of P0, which is the key value. And then if you work a little bit more, I want to speed up a little bit. If you work a little bit more, you will find that P of x is equal to, if I'm not wrong, 1 plus K0 delta bar, the integral between x 1 plus K0, infinity, and then g of z dz. So it is somehow up to some rescaling is the cumulative distribution of g, okay? So this is the result. And actually, I will not work, I will mainly use this result, okay? But if you work a little bit these things, you discover that when I was saying that F delta W converge when L goes to infinity to a value which is depends only on K0, okay, which is not, is deterministic, this value is 1 if you look, is the average force acting on the interface. This average force is 1 minus 1 over 1, so let me give you the result, is 1 minus the integral of x px dx, okay? Because remember that x is equal to 1 minus HCM minus HI minus WHI K0. Now when you sum overall I from 1 to L, Xi divided by L, 1 remain 1, this is 0, and this is minus K0 W minus HCM. And so it means that X average is equal to 1 minus the force. And so this is what you get here. This is X average. Okay? And so you have that the force is 1 minus X average. And if you do the calculation, what you obtain is 1 minus 1 plus K0 delta bar square divided 2 delta bar. And this is exactly what we didn't find, but we were supposed to find yesterday. I wrote somewhere, I think. I know, I erased, sorry. I know it's here. So in the force protocol, this is what you find. Okay, so I wrote the notes on the wiki. And now if you use these results and you compute X average using the by-part integration and so on, is an easy calculation, and you will find these results. And when K0 is equal to 0, you go to the critical force, okay? If you just replace K0 equal to 0, you find the value of Fc that you use with the other protocol. And this I recommend you to do, is not really difficult, and you can do it. But now I want to do the avalanches. Okay, so what we have done now, let me. Okay, so the idea is there was also the other calculation, okay, that shows you that is the critical force. So yes, okay, but then when you do just this, now I will do the avalanches, and you will see they become critical at K0 equal to 0. Okay, so let's see this. Okay, so now what we have? So we have two things. Let's say that we now have our distribution P of X that we know. So this is the distribution that in the stationary states describe the distance to instability. And let's go back to the case of L blocks. So we can pick L random number from this distribution, and this will be a good description of our system of L blocks. Okay, so let's pick L random number, and we sort them. So we draw L, I, D distributed, okay, distributed as P of X. Okay, so you pick them, you sort them, and so you will have X1, which is smaller than X2, which is smaller than X3, which is smaller than X4, and so on, XL. Okay, so this is the most unstable block. It's positive, but very close to instability. This is quite close to instability, and so on. Okay, so you can order them on a line. This is 0. This is the position of X1. This will be, let's say, the position of X2. This will be the position of X3, and so on. Okay, so you have your random numbers, and you order them, and then here you will have a lot of them because L is very large. But again, like in the RAM, we are interested in what is minimum, okay, which is close to the origin. Okay. And so let's imagine that we have a site x0, which is exactly equal to 0, so that trigger an avalanche. Okay. So this site will be stabilized. Okay. And so it will provide a kick to all sites, which is a random number that I call delta 1 divided by L. So everybody will be pushed of delta 1 divided by L. It's always the same thing. Let me write divided by L. Everybody will be pushed like this, okay? And now the big question is the avalanche going on? If x1 is smaller than delta 1 over L, then go on. You have a new restabilization. So we will have another kick. Kick delta 2 over L to everybody, okay? And now if x2 is smaller than delta 1 plus delta 2 divided by L, you go on. Okay? You understand how it works. Everybody, you check if the most unstable states that receive, so if it's the second one, receive 2 kicks. If it's the third one, receive 3 kicks. If they reach the origin, then the avalanche go on and on. Okay? So before to make more clear what is going on here, let's say that we have to compare the mean kick which is easy, is delta bar over R. And now the mean gap. The mean gap is the distance between these points. So where is the point x1? Okay, and here we have to use again the first relation that I gave you in the first lecture. So I say if you want to find the minimum, what you have to say is that the probability to draw a random number with the distribution P of x, draw a random number smaller than this x1 is equal to 1 over L. And this is very similar to the exercise I gave you with the chain, okay, the weakest link of the chain. This I can erase. So what we have, if you do this integral, again, you can use that for large L. You can use this also for this exercise of the chain. For large L, x1 is small. Is small. Because this is close to 0. So this integral is essentially the integral between 0 and x1 of p0 dx equal 1 over L. And this gives you that p0, sorry, that x1 is 1 over p0 L. Or pw, if you are not stationary, it will be pw. If it's stationary, it's p. So the mean, so this is the position of x1. Now the position of x2 is the same thing, but is 2 over L, because you have 2 random numbers in the bottom of the spectrum. And so this will give you that x2 is equal to 2pw0L. So what is, and you can go on, x3, x4, okay, there will be just this number that change, okay? So the mean gap, which is the mean gap which is xj minus xj minus 1 is equal to 1 pw0L. Okay? This is the distance that you expect between the very extreme of the spectrum. It will not be the distance, it has nothing to do with the distance in the middle of the spectrum, which is usually much smaller, okay? But the distance between the one which are most unstable, if you start from a distribution which is non-zero in zero, it is always like this, okay? So this is, it comes from the extreme value distribution. And so I was there, sorry, I was here. So we have that the mean gap is 1 over PW0 L. Okay? So again, we have to compare these two numbers, okay? And we have three situations that can occur. So if the kick is smaller than this, so we can remove L because it's in both sides. If the kick is smaller than this, which means if PW0 is smaller than 1 over delta bar, which was the condition for the denominator, okay? If this occurs, then you are subcritical. Because the kick are small, the gap are big, so giving kick, most of the time you are not able to destabilize more the block. The kick are small compared to the distance between unstable point, so you are subcritical. And you expect small avalanches. So it will stop very soon, okay? Let me erase all of these. Then there is the case, which is the critical case where we have the explosion. So when PW0 is 1 over delta bar, which corresponds to K0 equal to 0, okay, so this is, then you are critical. It is the critical point. And you expect power law avalanches. And I will say more about that. This is the case where you receive a kick which is of the same order of the gap. So every time is a fair competition between kicks and gap. On the other hand, if it happens this, then you are in trouble, you are supercritical, and the perturbation can spread all over in the system, and I hope I will be able to show it with a movie, okay? So then you are supercritical. But now we focus more on the critical case or close to criticality when K0 is very small, so in between these two. And so what is going on is the following thing. So let's go back to this, okay? So let's define random numbers which are IID. So let's define eta1 equal delta 1 divided by L. This is the kick. And this is the point you want to reach. So let me check again. No, sorry, I don't want to do that. I want to do 1 PW0L. So this is the gap. So let's take the kick minus the gap, okay? And now we go on, eta2 is equal to the second kick minus, let's say, the second gap. Eta3 is the third kick minus the third gap. And these gaps are always of the same order. So eta1, eta2, eta3, eta I are IID numbers. And if you look at the average when K0 is equal to 0 are exactly the same, so the average is 0. And so we can construct a random walk, xn, from I1 to n of the eta I, okay? These are capital X, okay? This is a random walk. And x1 is equal to eta 1. And so if x1 is positive, it means that you are able to destabilize the block 1. You can check, okay? If delta 1, if the kick, where I wrote that, if this is the first kick, if x1, which is eta 1, is smaller than delta 1, you go on. So it means x1, which is the difference between the first kick minus the position of the first point, is positive. You can go on, okay? So go on. x2 is equal to eta 1 plus eta 2. So it means that is the sum of the two kicks, delta 1 plus delta 2 divided by L, minus the sum of the two gap, which is the position x2. And again, if this is positive, go on. So when you stop when this random walk become equal to 0 or negative. So you stop when, for the first time, you hit the origin, okay? So there is a certain value n star at which xn star become negative for the first time. And the size of the avalanche S is the number, is delta bar, which is the jump of each, after each stability, times n star. So essentially, let's say that delta bar is equal to 1 for simplicity, okay? N star is the size of the avalanche. And we know that the distribution of this number decay with the power law, which is 3 by 2, okay? So the P of S decay like 1 over S 3 by 2, because it's the first spatial problem of the random walk. The random walk is symmetric. So actually there is a theorem. I don't know if you did the Sparre-Andersen theorem for the discrete random walk, but actually there is a stronger results for discrete random walk. So if you have, so it doesn't change the power, but it gives you the prefactor. So if you have a discrete symmetric, which means eta average is equal to 0, random walk, then the survival probability Q of n, which is the probability that you have not yet, as Abhishek was saying, not yet crossed the origin, is 1 over square root of pi n for large n. There is an exact expression at any n, but I just fix on large n. And as Abhishek was saying, if you want to do the P of S, what you have to do is to say, okay, I survived up to n minus 1, but I didn't survive, sorry, S minus 1, but I didn't survive at S, or better is S and S plus 1. And if you do that, okay, you have that, you have the 1 over square root of pi S minus 1 over square root of pi S plus 1, and you have to develop a large S, and what you get is the result of Galton-Watson we found yesterday. with the correct per factor, okay? And this result means that the avalanche in our mean field problem is actually a Galton-Watson process which is propagating, so you are really infecting the sites exactly like in the model Galton-Watson, and this gives you also the same prefactor. Now, let's say few things. Let me see the time. So I have 15 minutes. So I want to say two things quickly. The first one is what happens when K0 is bigger than 0. So you are a little bit subcritical. Then you can show, using the same technique, that if you add a tilt to your random walk, that the average depends on K0, then S max, there is a cutoff, and X max goes like K0 minus 2. And so what you will see is a power law. So S minus 3 by 2 divided the square root of pi 2, and then you will have an exponential cutoff S max that is due to the fact that you're slightly subcritical, okay? And this I will not prove it. Then I want to say one thing about mean field, which I think is important. So at the end, I solved mean field models, but there were two very different mean field cases. So the random energy model, I told you that when you have a directed polymer, which is a line in n dimension, when n becomes very large, then you converge to this replica symmetry breaking solution. So this is a one mean field. It means you have a line, but the dimension, so we say, let's say in general, you have h of x like this. So the dimension x is a dimension d, and h is a dimension n, okay? So this is a generic manifold, okay? In the directed polymer, so the directed polymer means d is equal to 1, is the time, and n is a number, okay? And when n goes to infinity, then you have a mean field model, which is RSB, and is one step. Okay. I call an interface, which we were looking here. The case d is a number, so n is equal to 1. H is a scalar, okay? But x has a dimension d, and when d goes to infinity, then you have the Galton-Watson. And if you do the equilibrium, you don't have the RSB, okay? So these are two mean field models. The Galton-Watson is simpler than the RSB, but they are different, and the dimension that goes to infinity is different. One is the external dimension, and the other is the internal dimension. So now, if I can show you, maybe I will show you what is going on so I will show just a simulation just to give you some motivation that this is an interesting subject. So yesterday I was, so here now we have a little bit, let me redo it again. What I have to do? So I don't know, it doesn't work. No, when it was like this, it was a good sign. Okay, thank you so much. Sorry for that. Okay, so I want to show this, what I showed yesterday. So this is the soft glass. And actually what is going on here is that people used to say that this blinking that I told you, these plastic events, are like the trap of my model. So we usually use this kind of models. It's just that the interface is what is called the plastic strain. And what you do is that when you have a plastic event, you just jump to the next well, exactly like this. The only difference is what is tricking in this system is that you have to do mechanics, which is something difficult. But so this is the example. So you are shearing the material. And so the rules, the only difference in the model is this one. So there is a site that becomes unstable. As before, it jumps, it gets restabilized of delta. So you can put 1 plus k0 if you want. And then all the other, they receive a kick. But now the problem is to derive these kicks is what is called the Eshelby kernel. Is quite difficult, okay? It's what you have to do mechanics. So it's a complicated kick that depends on the distance between the point I and the point J, and the angle between these 2 points and this line, or the straight line, because you did the shearing this way. So the first striking thing is that up to now, the kicks were all positive. So if the site became unstable, the other sites were more unstable. And this is what is behind the Middleton, is a derivation of the Middleton property, no passing rule, and is what makes the avalanche of the pinning abelian. While if there is a sign, the cosine can be positive or negative, it means so there is this side that becomes unstable, it gives positive kicks in this direction and in this direction, but negative kicks in this direction and in this direction. And so this makes the problem more complicated. But at this stage, 5 minutes after before the end, we will not enter on that. And you can just look at 2 cases. So these are simulations by Misaki Ozawa and in the group. We did it with the work with Biroli and Berthier. And so there is the preparation of the system. So the fact that you take a foam and you slowly quench down a small temperature, and you have something which is brittle, which is fragile, and something, if you do very quickly, which is very ductile, is contained in this form of the initial distribution. So a peak distribution, it means that in brittle gas, you have to imagine that the interface is done in such a way that more or less everybody see the same threshold, while is very broad in the case of ductile form. So let's see if I'm able to do in the correct way. No, I want to do first the other one. So let me try. First the form. So what I told now is more, no, I don't want this. I want this, oh my God. I would like to action this. No, okay. First you have to see the brittle gas. Sorry, so this was the supercritical case. So you see the green are the plastic events. So you see that you have a few plastic events, and then you have a gigantesque plastic events that invade all the system. The fact that it's horizontal is due to the Eshelby kernel that push in the horizontal and in the vertical axis. So this is what is called a shear band. And so at the beginning, you have some small avalanches, but then you reach, so the distribution somehow arrived here. It was super critical, and then you have a gigantesque events that occur. While in the other case, you will not have that, okay? And so you have only avalanches that occur, and at some point, the green means that you are fluidifying, and so at some point, you become, so it's this black curve, so you increase, this is W if you want, so you increase the deformation, but everything remain very ductile and very homogeneous, while in this case, you increase, and then when you arrive in, bump, you have this huge liquid that forms, and the other 2 parts remain solid. So this is to answer to Anupam, but then it's gone. That yes, you can have supercritical. So this is a real epidemic, with R0 bigger than 1 that propagates in the system, okay? So that's it. This is what I want to tell you. I'm sorry that I didn't do the last part of the exercise of the lecture yesterday, but more or less is everything. Mm. Yes, let's say that okay. So if the avalanche is, so here I'm more interested in the critical case. So when you stabilize a site of delta, because an avalanche S is in this fully connected model, I mean. In the fully connected model, the sites that become unstable are the sites that are most unstable at the beginning. So when you are restabilized, the probability that you are destabilized again is 0 because you are stabilized in delta, so you are safely positive and you don't become 0. In the lattice, in a finite system where you have a finite connectivity, it is not the case because the kick is not delta over L, which is a minuscule kick. The kick is delta over 2. So if you are neighbor of an unstable site, then you become unstable. So I like to say, if you are in bad companies, in finite dimension, it's more important of what you are, if you are stable or not. If you are in bad company, you will become unstable. While in mean field, it depends only on your state, and you don't depend on your neighbors. Okay? Thank you very much.